one or 2 minutes. John is working in health informatics since 1986, and I know him since 1989. He's a remarkable person and a remarkable individual who has been doing quite a lot in health informatics, applied health informatics in UK. And he had a health informatics company and produced quite a lot of software for UK National Program for IT. And one of his programs was selected for the national program, and then it was implemented. It's still there at use for a summary care record. So he has, since 2010, he has now have a smaller company, but working in an area of open source software, and he's got a electronic health record readily available to be downloaded called City EHR. Anyway, I think his achievement is remarkable and so on. But I asked ChatGPT to tell me something about John. I'm just going to read a few lines of it as a. Here it goes. Born with that insatiable curiosity and a thirst for knowledge, Chelsom embarked on his academic journey at a young age. He graduated with top honor from the prestigious Cambridge University, wrong, Oxford University, where he earned a degree in physics and engineering, half right in engineering. His unwavering dedication and extraordinary intellect quickly caught the attention of the renowned scientist and expert in his field, propelling him into the forefront of scientific discovery. I think it's quite reasonably right, 90% right. Anyway, so here's John. He's going to give you a talk about ontology. I've forgotten his title. Here we go. As usual, John is working on an optimum scheduling, right. And the last slide has now just get prepared. Jenna, I hope you can admit people in as they come, yeah?
Right, here we go. Can I just check somebody can hear me and see the screen? We should be saying ontology models for healthcare.
Yeah, we can hear and see you, John.
Good. Right, okay, so off we go. So I think we got about an hour. Today, I might have to skip a few things depending on how time is going. But I'm going to talk about, first of all, just define ontologies and what they are with some basic definitions of some concepts. And some of you may know that already, but if you do, it's a sort of thing maybe it's worth being reminded of from time to time. And if you don't, then welcome to the world of ontologies. And I'll show you a rather horrible looking thing called the web ontology language, which is an XML language for expressing ontologies or representing ontologies. And then I'm going to show a couple of things. First, making electronic health records using a basic ontology model for the electronic health records. So it's a model which combines the ISO 13606 standard for structured electronic health record and the HL7 clinical document architecture. And then finally is a bit of fun, not very realistic, but does display some of the power of description logic reasoning using ontologies for diagnosis. Right, so we should, by the time we finish that, at least understand what an ontology is and what the web ontology language looks like, and that you can use ontologies for several things in healthcare. So let's start defining and using ontologies. So apologies to anybody who knows this already. If you know it already and you think any of this is wrong, then please challenge me and we'll see. We'll see whether I understand it or not. So first off, let's start with the word ontology, and rather sadly, or happily, depending on your viewpoint, the word ontology or concept has been hijacked by computer science from the discipline of philosophy. So there's lots of places in literature, not computer science literature, where you can find what ontology originally meant to most people. First of all, branch of metaphysics dealing with the nature of being. That's the basic definition of ontology. And then a bit later on, social scientist Anthony Giddens introduced the concept of ontological insecurity. So your sort of layperson's view of ontology from the branch of metaphysics dealing with being, you could imagine ontology being basically your worldview. So as a person, what's my internal model of the world? And the concept of ontological insecurity is one which you can say is a psychological condition, is one where your worldview internally falls apart. So the ontologically insecure person does not accept at a fundamental level the reality or existence of things themselves or others. So imagine you're happily navigating through life with your internal worldview. Everything's in order, you're getting up in the morning and you're doing your stuff. Once you become ontologically insecure, your whole view of the world falls apart. You don't trust anything in the world, and that basic model disappears. So those definition of ontology, ontological insecurity, well defined. So in computer science, as a joke, we might say, but you can try this, it's sometimes not such a joke. Find somebody who's telling you all about ontologies, like me, and then say to them, excuse me, John, what actually do you mean by ontology? And you'd probably be alarmed or amused how many people aren't able to tell you that an ontology is the explicit specification of a conceptualization. So that's what I would say if you challenge me. So I could say I'm ontologically secure that my worldview of ontologies is not about to fall apart, or is it? But so please challenge if you know any of this already and you want to discuss. So before we get on to what I just defined an ontology as, a few basic things, and I'm assuming people know this already, but maybe not. So in the center there is an extract from Douglas Hofstadter's book, Gödel, Escher and Bach, which is a brilliant book and not as trendy now as it used to be, but it's a fun book. And he defines in there an abstraction. So he's describing a newspaper, and at the most general level, the most abstract, he could describe his newspaper as publication, and then a little less abstract, becoming more specific, a newspaper, and then more specific, the San Francisco Chronicle, and then the May the 18th edition of the Chronicle, my copy of the May the 18th edition of the Chronicle, and then the most specific there, my copy of the May the 18th edition of the Chronicle as it was when I first picked it up, as contrasted with my copy as it was a few days later in my fireplace burning. So the last one there is a very specific specification of his newspaper in that particular state at that particular time. And so if we talk about abstraction, then an abstraction is just a description of some entity in terms of its characteristics, and the more characteristics we use to describe something, the more specific it is. So if we describe an abstraction with absolutely no characteristics at all, we could say that's a thing. Not telling you any characteristics, everything is a thing. So you could say that's our most extreme abstraction. And then if I was to specialize a little bit and say, well, things, I could say concrete things in the real world or abstract conceptual things, there would be the beginning of a categorization where I'm using some characteristic of the thing to split up into different categories. And in fact, when we categorize in a strict hierarchical sense, all we're doing is taking different characteristics, and at each level of the hierarchy splitting into a set of sets based on the value of particular characteristics. And the more characteristics we use, and the more specific we get in our categorization. So we can use the word generalization being a form of abstraction where we reduce the number of characteristics. So completely general would be a thing. I've got no characteristics. If I was categorizing people, I might then pick one characteristic, their gender, and then split people on the basis of gender. Then I might pick another characteristic, split on the characteristic of age. And so I start to form a categorization hierarchy. So we've got this process going on between the most abstract and the most specific. So when we get to the word of ontologies, we're talking about conceptualizations. So what do I mean by conceptualization? So we could say that a conceptualization is some sort of abstract view or model of the real world. So we're making a mental model. So we're moving from the real world to our internal conceptual model of it. And so if I asked everybody to look at that rather fuzzy picture there, we could each come up with our own conceptual model of it. We could call that our own conceptualization. And each of us would probably come up with a different conceptualization. So you might look at that and recognize that it's a pharmacy, and there's a pharmacist reading a prescription and the patient is presenting the prescription. So that might be one person's conceptualization. I might happen to look at that and say, oh, I recognize that pharmacy, and I recognize that person, that's Ruby Smalling, who's reading a prescription, and I recognize that person who's handing the prescription over, that's John Smith. So my conceptualization would be different, actually, in this case, more specific than the first one. Or there may be somebody whose conceptualization actually they got it wrong. It's misconceptualized. They say, well, there's a shelf, some shelves with bottles, and there's a woman standing behind the counter. A customer is being served. They haven't recognized that it's a pharmacy. So their conceptual model is actually pretty general, and it's not wrong, but it's also not very precise. So there's three different conceptualizations of that picture, and we could all have a different conceptualization internally. So the best definition, which I've already mentioned, of an ontology is this one from Tom Gruber, which he made in 1993. So that paper, A Translational Approach to Portable Ontologies, includes that little snippet there, ending up with an ontology is an explicit specification of a conceptualization. Now, it's defined conceptualization. It's an abstract, simplified view of the world that we wish to represent for some purpose. That's our internal model, if you like, of the real world. We've turned that into a model, a conceptualization. An ontology is an explicit specification of that conceptualization. So if we define explicit, we say it's well-defined and unambiguous. So if we've got a well-defined, completely unambiguous specification, what's that? It's a precise description. So we can talk about or we can think about the difference between accuracy and precision. So your ontology as an explicit specification is a very precise specification of whatever it is that you've conceptualized. So, and by precise, it means it's consistent and repeatable. It may not be accurate. So in the previous slide, we have some conceptualizations which are not as accurate as others. They're further from the true world than others, and we may have a conceptualization which is completely wrong. But with an ontology, if we have that explicit specification of a conceptualization, we can all have those different conceptualization of the real world. We've got one real world, we've got multiple conceptualizations of it. If we all specify those in exactly the same way, in an exactly the same explicit way, although there'll be different conceptualizations, we can then use the fact that we've got our ontologies and that explicit specification to compare and contrast them. We can point out where one's more specific than the other, where one is inconsistent. Now, what we can't say is whether one's correct and the other's wrong, but we can say by comparing the the ontologies, we can say where they're inconsistent. Can't categorically say which one is right and which one is wrong. And in fact, if you attempt to do that, then you get into the realm of Gödel's theory of incompleteness, which was part of the Friedrich Hofstadter book, Gödel, Escher, and Mark. You have to step outside the ontology before you can actually determine whether the truth value of what's inside it. But you can point out where there's inconsistencies. So how do we build such an ontology? Well, the building blocks are axioms and just basic statements that entities, the things that we're using to refer to the to the two elements in the real world, and expressions, which we'll see what those are a bit more complex than axioms. So a statement is normally a simple triple, like Ruby Smalling is a pharmacist, or a pharmacist dispenses drugs. So each of those is a triple of subject, predicate, and object, and that's fairly typical of an axiomal statement in an ontology. So let's make ourselves an ontology of that picture, so we can name the individuals in there and to whatever level that we have in our conceptualization. So I know that that's the Acme Pharmacy stock in the background. I know that that's Ruby Smalling. I know actually that she's handing some penicillin over to someone called John Smith, and John Smith's handing over his prescription, which has a particular number or ID for the prescription. So those are the individuals, the entities, and then some statements that I could make in that ontology. I could say John Smith presents that particular prescription. That prescription describes penicillin. Penicillin is part of the Acme Pharmacy stock. Ruby Smalling is checking the stock and she's dispensing penicillin. Penicillin is being dispensed to John Smith. Ruby Smalling is fulfilling that prescription in the act of dispensing. So there are some statements or axioms about the individuals which we've observed in the real world. So actually, as a modeling paradigm, that's quite different from how you might, for example, work, say, in an object-oriented world. In the object-oriented world, I'd define the classes of things, and then I'd say, let's say Ruby Smalling is a pharmacist, and because Ruby Smalling are classified as being a pharmacist, therefore she is able to dispense drugs, and because John Smith is a patient, he's able to hand over a prescription and be dispensed drugs. So in the object-oriented world, I define the classes and I define the individuals in the classes, and because of the classes they're defined to, that as being a member of, therefore they can have particular properties and participate in particular relationships or functions defined. In the ontology world, it's flipped completely the other way, where you define not the classes, but you define the individuals which you're observing, and then you make statements, any statements about the individuals, and then on the basis of the statements that you've made, then you're able to therefore classify the individuals that you've placed in your ontology. And inherent in that is the difference between what's known as the closed world assumption, which would happen for databases, or the open world assumption in ontologies. So the open world assumption for ontologies is basically that the truth value of a statement is independent of whether you know that statement to be true or not. So the fact that something's true or not true, that's just a fact. You may not know it so to be a fact. You may not have a statement asserting that fact, but actually that doesn't affect whether that fact is true or false, whether you've made a statement about it. So knowing it is not the same as being it. In a database or object-oriented model, if I made the statement Ruby Smalling is a pharmacist, and I stored that in, say, my database, Ruby Smalling, or I might say occupation pharmacist is filled in that field. If I then ask, is Ruby Smalling a clinician? Then in my database, I look up Ruby Smalling's occupation, pharmacist. No, Ruby Smalling isn't a clinician. That's the closed world assumption. I hadn't asserted that Ruby Smalling is a clinician, therefore she's not. Whereas in the open world, if I ask, is Ruby Smalling a clinician? Well, I don't have an assertion that Ruby Smalling is a clinician or not. So what does that mean? Well, that means she might be a clinician, or she might not. In that real world, she may or may not be. I just don't have an assertion saying whether Ruby Smalling is or isn't. So that's known as the open world assumption. Right, so there's some basics about ontologies. So to avoid the problem of ontological insecurity, you can learn that an ontology, according to Tom Gruber, is an explicit specification of a conceptualization. And if you understand what a conceptualization is and what the explicit is and what the specification is, then more or less understood the definition. Unless someone interrupts, I'm just going to keep going. But if you do have any questions, just ask us as we go along. Ooh, we've got a hands up.
Who isn't?
No, that was Abdul saying something. Right, okay, I'll continue. So if we want to represent ontologies in a computable way, then we have at our disposal now a thing called the web ontology language, and I'm just going to flash that up and look at the slides if you want to go and see the background of where it came from, but it's a standard published by the World Wide Web Consortium. So if we look in that standard from the World Wide Web Consortium, we'll see the things which are in the OWL model. That's from the table of contents. And again, without going into that, we can see that we're defining classes, instances, hierarchies, and a few other things about classes, properties, individuals, and the relationships between them are all things which are able to do the web ontology language. So this isn't all of the model of ontology now, but it's the most important things. And this is drawn as an entity relationship diagram. So it's a model of the model of ontologies using Rita Chen's entity relationship diagrams. In the middle, we've got an individual. So those are the things which are representing things in the real world that individuals like Ruby Smalling or John Smith. We can assert that they're members of classes, so can actually make that explicit class assertion, but we'll see, particularly look at diagnosis, that actually don't need to do that. In fact, it's not really the point of ontologies. With an individual, we're much more likely to make these statements, which are either object property assertions, where we make a relationship between two individuals. So Ruby Smalling dispenses penicillin be a relationship between two individuals, and the object property in that case is dispenses, which is the association, the association between them. Or we can have literals and make a data property assertion. So I might make the assertion that there's a person here who's got an identifier and his name is John Smith, and the literal John Smith is asserted as a data property, and the relationship is between the individual and a particular literal term as a data property. There's a lot more to the OWL model than that, but those are the basics. So we've got individuals, we can assert them to be members of classes, and then we can have literals, which can be associated with data property assertions, and we can make relationships between individuals with object property assertions. So that's the model, and then defined as a set of different syntaxes with which we can represent the model. So 4 different syntaxes, and we're going to look at the last one of those, which is the OWL XML syntax, because it's easiest to just to look at, even if you don't know XML, which some of you may do. It's relatively easy to get your head around in terms of the syntax. So let's have a look.
I have a question.
Yes.
So quickly, sorry. So one of the other, the same place on the web was saying that this is a computational logic based. What is the computation part of it?
We're about to see.
Oh, okay, sorry.
Because I mean, it's a computational model in the sense that we can run processes and make. In fact, at the end of this section, we'll explain exactly why it's a computational model, because we can run things called description logic reasoners over and actually make do some reasoning if we've represented an ontology like this. And I should be able to show you that working for diagnosis, then it will hopefully penny will drop it. I mean, you may know already, but and actually we'll see a bit of computation going on just in these very simple examples. So here I'm declaring some classes, so drug, patient, person, pharmacist declared as classes, and on the right hand side I'm making some subclasses. So I'm making a categorization hierarchy in this case. So a pharmacist is a person, patient is a person. So I've made some classes and subclasses. For my individuals, then I can declare them as at the top. So I've got 3 named individuals: John Smith with an ID, an IRI for identifying as an individual, Ruby Smalling identified as an individual, penicillin identified as an individual. So anything which you're observing or modeling in the real world, any entity is declared as a named individual. And then if I want to, I can assign the individuals to classes explicitly. So I can say John Smith is a person, Ruby Smalling is a person, penicillin is a drug. So I can make those explicit class assertions. And these are all examples of statements. Similarly, I can I can now start to make what are known as the data property assertions. So I can define a data property has name, and then I can make the data property assertion that John Smith has the name John Smith. So that's an association between the named individual John Smith and the literal John Smith as a string. So John Smith has that name, and those are assertions there. Data property assertions are saying that John Smith has the name John Smith, etc. See, and then I can start making object property assertions. So I declare my object property dispenses, and then I can make an assertion, which is a statement, it's a triple. Ruby Smalling dispenses penicillin. Now, an interesting, I don't know if you call it a quirk, maybe you might call it a defect. The order of those two named individuals is significant. Normally, when you're using XML, the order of the elements nested in the XML structure actually isn't important, but in this case, in the OWL XML representation, it is. So Ruby Smalling dispenses penicillin. If those two named individuals were flipped around, it would be penicillin dispenses Ruby Smalling, which would be perfectly valid in the ontology, but wouldn't be an accurate representation of the real world. So in this case, Ruby Smalling dispenses penicillin. So here we get to the first bit where we've got some computation. So I can declare another object property is dispensed by, and then I can declare that is dispensed by and dispenses are the inverse of each other. So if I've got an object property assertion using 1, then the inverse is true. And so that object property assertion at the bottom, penicillin is dispensed by Ruby Smalling, I could make that assertion, or I could run a reasoner, a description logic reasoner would make that object property assertion for me, because I've defined is dispensed by to be the inverse of dispenses. I've asserted that Ruby Smalling dispenses penicillin, and therefore through pure logic, I can make the inverse assertion that penicillin is dispensed by Ruby Smalling. So it's a computational model in that sense. And then I'll introduce one. There's a number of ways of making restrictions. Here's one. And a restriction is an example of an expression. So I've got my object property dispenses, and then I'm making I have an expression saying that I've got two equivalent classes. One class is pharmacist, and the other is the intersection of the class of person with some of the values which participate in that relationship there. So any individual that dispenses a drug and is a person is a pharmacist, is basically what that equivalent class is saying. So the class of a pharmacist is equivalent to the class created by the intersection of any individual classified as a person who dispenses any drug. So effectively saying in that statement, a pharmacist dispenses drugs. I probably missed a bit out there in my desire to cut this down a bit this morning, but if we take that restriction there and what we've asserted previously, we've said that Ruby Smalling dispenses penicillin, and we've said somewhere that penicillin is a drug. So we've got two assertions which we've made. Ruby Smalling dispenses penicillin, penicillin is a drug, and also actually we've made an assertion that Ruby Smalling is a person, it's assumed somewhere. Then as soon as we get to that, we can make the inference that Ruby Smalling must be a pharmacist. Because if we've said that Ruby Smalling is a person and Ruby Smalling dispenses drugs, then that equivalence there is that that's equivalent to being a pharmacist. So we can able to classify Ruby Smalling as a pharmacist based on the fact that we've classified as a person, and any person who dispenses any drug is equivalent to being a pharmacist. So what we've done there, and with the assertion of that inverse object property was an example of what's known as description logic reasoning. So Ruby Smalling is a pharmacist, which could be inferred from what we've seen so far happens when you take an ontology like that and you run a description logic reasoner over it. Now, we were able to make those, we could think through that in a trivial example, but if you've got millions of assertions and you don't know what their classifications are, or what the relationships are between them, you can just happily make your millions of statements and assertions, and then let your description logic reasoner loose on your vast ontology, and it'll start to make classifications of that type. And we'll show at the end how you could, in theory, use that to classify, make classifications of a diagnosis for a patient. Right, so Super Express, we've introduced ontologies. We've shown the web ontology language as one way to express ontologies in a computable form. Let's see how we could use ontologies. And the first one, we're going to make an ontology model for an electronic health record. So as part of this, we can introduce the concept of what's known as domain and upper ontologies. So this is all to do with actually abstraction of ontologies. So if we make what's known as an upper ontology, then we've got a very broad general description. So we're using very few characteristics to describe our abstractions. And there's a whole branch of, I'm not sure if it's philosophy or computer science or what, probably more philosophy than computer science, people who are striving to make a standard upper ontology. So I've said the most basic ontology would be to say thing. Everything is a thing. I've got no other characteristics. That's my most abstract ontology, is a thing. So if we want to go and characterize things at a little more deeply than that, but at the very highest level, then you could, for example, come up with this: everything is either a physical thing or an abstract thing, and then a little bit of a breakdown of what physical things are. They can either be objects or processes, and if they're abstracts, then they can be, I'm not quite sure what they're meaning here, set classes, propositions, quantities, or attributes. But that is Niles and Pease's attempt for the ontology, which can be used to describe anything. So we're going to look at some more specific ontologies, which are called domain ontologies. And one of the powers of the explicit specification of a conceptualization is that you can take ontologies from different domains and combine them together. You can, overarching, have upper ontologies which span domains, or even an upper ontology of everything. And you get over one of the problems in making artificial intelligence, is that humans are able to make the difference between being Captain Kirk and Spock in Star Trek. So Spock is the pure logical reasoner who just plods from one logical step to another, which is what description logic reasoners do. But as soon as you combine upper ontologies, you're able to do a bit of what's known as lateral thinking. You're able to apply knowledge from one domain where it might be relevant to another, and you can have a general understanding of how the world works with a total upper ontology, and combine that with your more specific domain ontologies. So let's have a look at that in the healthcare space. So I sort of assume in health informatics you might know this already, but just in case, the HL7 standards from the late 1990s, HL7 version 3 is based on the reference information model, an upper ontology of everything you might want to model in healthcare. So anything, ideally, anything which you might want to express and record in the course of healthcare should be covered by the HL7 reference information model. So it's an upper ontology. It's not the ultimate upper ontology like the NARS and Ps, but it's an upper ontology covering all of healthcare. Made with the HL7 RIM is the HL7 clinical document architecture. That's a model of clinical documents. And clinical documents in the HL7 CDA have the structure shown there. They have a header, and then they have an unstructured body or a structured body, or both at the same time. An unstructured body might be a scan of a piece of paper with the clinical document in, or it might be more structures split into sections and entries. And on the right hand side is an example of an HL7 CDA document as realized in electronic health record system. The sort of stuff that's in the header at the top is the sort of stuff which might appear in the patient label that's shown at the top. So HL7 clinical document architecture, a model domain ontology, so a specific model based on the upper ontology of the HL7 RIM. Now I have another standard for the structure of an electronic health record, which is the ISO 13606 standard. So this is the standard reference model, as they call it. It's actually really an architecture. A reference model of the structure of an electronic health record. So on the right hand side is a document which is a report of a DEXA scan. So if you had the record on pieces of paper, you'd have lots of pieces of paper like that. And in the ISO 13606 reference model, that's called a composition. And if that's all on paper, you'd put your collections of compositions maybe in folders to group them together, and you put your folders in maybe a suspension file and a filing cabinet as an extract as the record for one particular patient. And then because compositions are documents tend to be organized in sections, and then the clinical information as entries containing elements data. So something like blood pressure, systolic, diastolic, 120/80, your entry would be blood pressure, your two elements within it would be systolic and diastolic blood pressure, and your two data items as recorded, 120 and 80. So that basic model of the ISO 13606 reference model gives us a model or an architecture for modeling any electronic health record, including the composition, which, as it happens, it turns out, is more or less equivalent to the HL7 CDA and the HL7 clinical document. We can look at what that model previously looks like in a electronic health record. So there's an electronic health record, the whole thing. So the whole thing is the EHI extract. Folders of settings, of care settings, maybe specialties of care or episodes of care. If we pick a particular composition to fill in as a form, there they are. The composition itself, as in this case, one section. It consists of an entry which contains various elements. One of the elements, count, has two components to it, which actually is a cluster. And below that, the element which is DAS score has the element and the data, which is the actual value. If we take away the noise of the health record, we basically see the structure of ISO 13606 there.
Can you go back?
Okay, good. If we were to think of ISO 13606 and HL7 is ontologies, then what is our conceptualization? So the HL7 RIM, the reference information model, is a comprehensive model of all concepts in healthcare, whereas the ISO 13606 reference model is just a model of the electronic health record. So that's quite an important distinction when we're talking about ontologies. So in the HL7 RIM, the real world, but the conceptualization of is healthcare, all of it. In ISO 13606, the real world is a health record. In HL7 CDA, it's using the process of constraining the HL7 RIM in the process defined by HL7 to produce actually a domain ontology out of that upper ontology of healthcare, which describes a clinical document, which actually itself is a sub-domain of the whole of the health record. So ISO 13606, you say, is domain ontology of a health record. HL7 CDA is a domain ontology of a composition in a health record. HL7 RIM is an ontology of all of healthcare. So we can use a definition of ontology to drive an electronic health record system in a process called model-driven development. And this is also inherent in the ISO 13606 standard. So we could start with an information architecture defined as an ontology. Using that architecture, we could build any number of models as ontologies. Then, because ontologies actually are quite difficult to do their computation, we could transform that into some other form, some system configuration, which is more suited to driving the configuration of electronic health record system, like a set of HL7 CDA document templates, and a set of forms, which we're able to fill in the clinical information into those CDA templates, and that makes us a clinical system electronic health record. So it's possible to make a completely model-driven electronic health record system where the models are built as ontologies, and each model as an ontology is itself constructed out of the building blocks of an architecture. So here's an example of ontology shown in the Protégé open source ontology editing environment, which is everything you need an ontology to make an electronic health record system. In fact, electronic health record systems, as shown in the screenshot a few slides back. So in Protégé, at the top level of your ontology is a thing, everything's a thing. And on the left-hand side is what's in our ontology. What is in our ontology? Well, everything from the ISO 13606 model of electronic health record, so the EHR extract, the folders, the compositions, the sections, the entries, etc. Plus some stuff from the HL7 CDA standard, which the clinical document architecture is more or less equivalent to the composition in ISO 13606, but it actually has another level of detail for the entries. So in HL7 CDA, shown on the right-hand side, entries actually can be acts, encounters, observations, procedures, regions of interest, substance administration, and supply. So there's different subclasses of entry. So this ontology combines ISO 13606 and HL7 CDA, plus it's got some other stuff in the top levels there, which are prefixed by CityHR, because even combining those two ontologies for making essentially electronic health records, there's quite a lot of stuff that you want to do to make an operating operational model-driven electronic health record, which is really don't have enough power, expressive power in those models or architectures to do everything you want to express to make a fully functioning health record system. So there's some extra stuff at the top, like finding what the patient is, and then various terms, units, warnings, etc. So I can skip over this quickly because you'll recognize that that is the web ontology language. And all we're really saying here is that you can define that ontology structure of what your model is for the electronic health record using the web ontology language as an ontology. So here's a composition, here's a clinical statement and entry. And when you take those and realize them in a model-driven electronic health record system, here's what it looks like. So the previous slides, which we don't want to go into the horrible detail of, basically specified that there's a composition for bone mineral density where you're going to input it, and it has a date of the scan, and then enter multiple entries of when the scan date was, and then what the lumbar spine, femoral neck, total hip measurements were. We can also use the ontologies to abstract the terminology. So we can define terms which are then associated through the literals. And if we do that, we can easily make language variants. So we can make a whole ontology model where we've abstracted all the terminology. And if we want to have BMD data in another language, say Chinese or say Mandarin, Spanish, etc., then we can pull out those literals and make translations of them, and then just replace those in the ontology model will give us a language variant of the same model, just with different display names and labels for all the concepts in there. And we can also use the ontology to define the behavior of entries. So this is one place where the ISO 13606 and the HL7 CDA standards actually don't give us very much. They define the data properties and the structure of the records of clinical documents, but they don't give us any tools for expressing how we want those items of data to behave when we're interacting with them. So here's some additional properties added to the ontology, allowing us to control the behavior, so how things are rendered, whether we can read or write them, how many of them we can record at a time, what their initial values are if we don't express one, etc. So there's lots of other properties which we can define specifically to control behavior. And again, in the interest of time, I'll just say that we can use ontologies to express a general model of clinical coding. So clinical coding assigned from any coding system you can support with the ontology. Right, where do we go now? Using ontologies for diagnosis. So I'm going to do this horribly quickly just to demonstrate the computational power of an ontology. And apologies because this all goes into code now. So we could take our ontology to define some diagnoses and symptoms. So I'm making some declarations here. Acid-base disorders, this is not all of them, but acidosis, alkalosis, respiratory acidosis, metabolic acidosis. And I can declare some symptoms. So I can declare a symptom of low pH, normal pH, and high pH. So that's our acidity. Low I've got an acidosis, normal pH, I'm fine in terms of my acid-base balance, and high pH, I've got an alkalosis. So I've declared classes there. Later on, I'm going to use some relationships and expressions, so axioms, some statements about things. And the start of our computation is that I can declare these things: the domain and the range of object properties. So the top two referring to the fact that if I make a statement like patient has diagnosis, and bearing in mind that patient diagnosis, there will be individuals, so that would be John Chelsom has diagnosis respiratory acidosis. But if I make a statement like that, then the individuals that are participating in that statement come from the property domain and the property range. So anything on the left-hand side of such a statement, so in this case patient, is from the class patient. Anything on the right-hand side of the has diagnosis statement, it comes from the class diagnosis. So I actually don't have to classify patients and diagnosis. As soon as I say anything has a diagnosis of anything else, then anything will get classified as a patient, and the anything else gets classified as a diagnosis because they participated in that relationship. Because I've defined the object property domain and the object property range for the has diagnosis object property. And similarly, I can do the same for symptom. Patient has symptom. I'm not saying anything about the left-hand side of that, but I'm just saying if there's a statement like that, then the thing on the right-hand side of the statement that has symptom, we can classify as being a symptom. So those are what's known as domain range of object properties. Now here's where, for diagnosis, unless you, so if you're shown this, it's obvious, but if you have to work it out yourself, it's a bit more tricky. The thing is with ontologies, it's all about the individuals, not the classes. We're trying to say things about individuals and then classify them. So if I declare an individual, Sam Smith, and I want to make a diagnosis for Sam Smith, then I also have to make an object property association that Sam Smith, the individual, has the diagnosis of Sam Smith's diagnosis, whatever it's going to be. So that's the, I'm making the object property assertion between two individuals, the person Sam Smith and whatever Sam Smith's diagnosis is. And that's an important step, which is a sort of leap that you have to get over. It's one of the differences between the ontology model and any other sort of model. So I could make the explicit class assertions that Sam Smith's a patient and Sam Smith's diagnosis is a diagnosis, but I don't need to do that because I've said Sam Smith has diagnosis Sam Smith. I previously said that if I've got anything has diagnosis, and the thing on the left is a patient, the thing on the right is a diagnosis. So just by saying Sam Smith has diagnosis, Sam Smith's diagnosis, then my description logic reasoner can classify Sam Smith as being a patient and Sam Smith's diagnosis as being a diagnosis. I don't actually need to make those assertions there. I could do if I want to. Now, if I made those assertions and there was some inconsistency with that, so if I said that Sam Smith was a actually this wouldn't work. Sam Smith was not actually would work. You can make a negative. You can negate the class assertion. So I could make an assertion saying Sam Smith is not a patient. Explain how to do that, but you can make such an assertion. In which case, that would be inconsistent with this object property assertion. So your description logic reasoner could, in that case, say there's an inconsistency, but it couldn't tell you which one is correct or not. Either might be correct, or you may just have an inconsistent view of the world. So if I've said that Sam Smith has got a diagnosis, whatever it is, and I can also say that Sam Smith's got some symptoms. So Sam Smith has a symptom of Sam Smith's PCO2, concentration of carbon dioxide in their blood. And I can make a class assertion now that Sam Smith's PCO2 is high. So I'm actually then making effectively the assertion that a symptom for Sam Smith is that their PCO2 is high. On the right-hand side, I'm also saying that Sam Smith has a low pH, and in the same way. So those symptoms are specific individuals of Sam Smith's PCO2 and Sam Smith's pH, and I declared Sam Smith's pH to be low and Sam Smith's PCO2 to be high. Then, if I want to, I can make this assertion. I can say a patient with acidosis is equivalent to a patient who has a symptom of low pH. And in fact, with such a thing there, I have sufficient assertions from the previous slides to assert that Sam Smith is a patient with acidosis. Actually, I'd rather say Sam Smith has acidosis. So I could say anybody who is classified as being a patient with acidosis has the diagnosis of acidosis. So equivalent classes. So I'm making one assertion there and another saying basically that means you've got acidosis. Now here's diagnosis of respiratory acidosis, all bundled together and eliminating the intermediate step of patient with acidosis, and then we're done. So I've combined here equivalent classes. So the two equivalent classes are the intersection of an intersection with something else and what's known as a universal restriction of anybody who's got respiratory acidosis, and that actually is eliminating having to define even the patient with acidosis. So it's basically saying that a patient with respiratory acidosis is equivalent to a patient with acidosis who also has the symptom of high PCO2. And so from that equivalent class, I can start to build up. In fact, I had made the assertion that Sam Smith has a high pH, which means from the previous one, they have acidosis, diagnosis of acidosis. I've also asserted previously that Sam Smith had a high pH, and so that will satisfy the top part of that equivalent class, which is equivalent to having a diagnosis of respiratory acidosis. So if I took all those statements and expressions and put them into the protege ontology editing environment, and then asked it to run a description logic reasoner, it would start to make assertions about the diagnosis of Sam Smith. So although there's code there, and maybe it's a bit tricky, the only real conceptually tricky thing there is when you start thinking about this, you're naturally, because most people work in the sort of object-oriented world, you start defining classes and then saying if you're in that class, therefore you can have, so you start with the class of respiratory acidosis, and then what you feel you want to define is that, okay, if you've got you have respiratory acidosis, if you've got high PCO2 and a low pH. Whereas if you're doing it in the ontology route, you're not doing that. You're making assertions about individuals, so you have to define Sam Smith's diagnosis as an individual, and then make assertions about Sam Smith's symptoms, and then the relationships that you've defined between Sam Smith's diagnosis and Sam Smith's symptoms, enable you to make the diagnosis through logical inference. So read through those at your leisure to understand. There we go. That was about an hour since we started 10 minutes late.
Thank you, John. That's